Okay, right. So again, one more time, trying to make sure that you guys are aware of what's being tested. Right, let's kind of like do a big um what call it recap, right? Kind of like a consolidation of all the things that you probably need to figure out. And welcome you back to term three. Actually, no, I've been seeing you guys over the holidays also. So June is always like that, right? It's never a real holiday until year five. Yeah, I mean year five June holidays will be a real holiday, right? Yeah, I mean I still do see my year fives during the June halls, but you know half of them like half a week. So yeah. But you guys can't because you guys got the like you know your major exams is this end of this year, right? So year five most of them don't really care that much, right? Which is why they only panic when they're in year six. Mechanics is one to six. If you look at the like kind of like just to give you like an idea of what your topic structure is like. Okay, one to six is mechanics. Like anything to do with like energy lah, force lah, moments lah, pressure lah, right? Movement lah, right? Power lah, all that, right? It's all here, right? Mass rate, dynamic, everything. These are mechanics. Okay. Then you got three chapters of thermal. This is one, two, three. These are the three chapters of thermal. We revised 7 and 9, we didn't revise 8, right? Thermal processes, which is conduction, convection, radiation. Again, you think you know, but you know, that's where a lot of students will make mistakes also. Right? And then that's 7, 8, 9. And then after that, you got 10, 11, 12. These are waves. So you got three chapters of waves, right? Expertly disguised as three chapters because they basically had a fourth chapter before. It's called sound. They put sound into wave property. So general wave property is now very big, right? So 10, 11, 12, three chapters. Okay, so you know they try to they try not to scare you lah. You know what? Wow, 20 plus chapters, but actually they can make one chapter very big, right? And then they say that yeah, it's still less than 20 chapters, right? Anyway, so then at the start of this year we had this whole big long thing. Okay, so nuclear has this sorry. At the start of the year we had this whole big long thing. So we have this all the way from static electricity, current electricity, practical electricity, magnetism, electromagnetism. So you're telling me that your school is on magnetism now, and your school is on practical electricity. So like which part of practical electricity are you on?
He's gonna do like the safety, the live
Safety?
wire,
So that means you're almost done, right? Safety, yeah.
like safety and the live wire, neutral wire.
Circuit breaker?
Yeah, he's
Okay.
just
Once you hit circuit breaker, it's about the end already. Then for magnetism, he just started. He just started. Did he do anything else? Change teachers? Term semester change teachers? Huh? Who's this? Who's this? Who's this new one?
yeah. She's really good.
Chill. She doesn't care.
Because we had like one lesson before the test, and she didn't do it. She just tested out the test first, and then like uploaded the answer and the class.
Oh wow. Wow.
And she's really
Oh, she's really nice. Okay. Yeah. Right. Nice doesn't get you sevens. Okay. I'm not nice, and I'm happy to be not nice. I don't care whether you like me or not. I just care whether you get your sevens. Okay. Was it? So yeah. In fact, we already went past electromagnetism, and we are now on electromagnetic induction. I guess one of the reasons why like it seems I'm so fast is because electromagnetism doesn't have much definitions. There's not much definitions. Doesn't have much equations also. Like practically everything about electromagnetism was what? Right hand grip rule, left hand rule. That was pretty much it. Right? And how many questions you want me to do of this? Right? Of course, the last thing that we did was for electromagnetism was DC motors. Right? DC motor is a motor, right? Yeah, which is this one here, which unfortunately doesn't work anymore. I don't know why I'm so sad. I changed the battery. Look, it just died on me. This thing doesn't want the motor anymore. But it's a motor. I guess you can understand what this does, right? It's a portable fan. Doesn't want to spin. Spin, damn it. Okay, so anyway, yeah, there you go. So there's the DC motor. It died. It just means I have to buy new ones, right? It's not omen or anything like that. Question: did someone drop it? There you go. Okay, and then we basically are going to do electromagnetic induction. Okay, and then you have to do me a favor. You have to check with me whether your school is doing radioactivity. So you see, right? The idea here is that the O level stream started doing radioactivity last year. Last year was the first year, right? And then suddenly some of the IP started to do radioactivity also. You know, kind of like they have to try to keep up, right? You guys are considered IP lah, like you know, in a sense, right? I mean, like integrated program, you are integrated into the system, right? Okay, so you guys are like IP equivalent. Yeah, but you know, so and then IP means what? IP means the teacher do what they want to do, like your chill teacher, you know, they just do whatever the heck they want to do. So for the year before, radioactivity was included. So Laura Lang had to do radioactivity, and then the 2 years before, right? And then the last year, which was just you know 1 year before, 2 years ago they had to do it. Then last year they cancelled nuclear. So I don't know what's gonna happen to your syllabus also. Yeah, see, so they kind of like they want to do whatever they want to do. So you just sit in for induction, and then you just try to figure out whether or not you're going to be doing nuclear.
I don't know, like it's gonna take ages before you pass it. I think I rather just sit in.
Ah, okay.
And then if I get it tested, then
Would you know for you guys? It's in, is it? It's in for you guys. Okay, so I'll tell you this. Okay, you sit in. It's written in syllabus, but it depends on whether they are. Oh, what the hell?
So sometimes they suddenly take out the last chapter.
That's so annoying.
We still haven't even learned moments properly. It was supposed to be taught last year, but then they skipped it.
So you gotta understand, like you know, you going into IB, all of you are going to IB, right? Moments is a big thing now. I mean, in HL physics, I mean, if you decide to do SL physics, then you don't have to care about moments anymore for the rest of your life, which is fine. Yeah, but yeah, if you're doing HL physics, then yes. Okay. Anyway, so EMI, can right? EMI is this is the second last chapter. I don't know what's wrong with my chapter number. I don't know why is it 22. It's supposed to be 19, right? Second last chapter. Last chapter is radioactivity. Okay, completely off sequence though. You look at this, right? This is like what static, then electricity, then magnetism, then mix electromagnetism, then electromagnetic induction. Then suddenly one nuclear physics. Yeah, you know what's the irony of it? Like this is not a new topic, you know, to O levels. Nuclear physics used to be in the O levels in Singapore, like in the 1990s lah. Shut up. Okay, so in the 1990s, like nuclear physics was in, okay, and then they brought it back. So they took it away for a while and they brought it back. It's like what's with this cyclic nature thing, right? But one thing that I do notice is it's worse now. Like I was looking through the syllabus, I was doing some of the practice questions, I was like, how come it feels like it's like harder than what I did when I was in secondary four, you know? So it does feel like there's actually a lot more detail now. Okay? Oh well, right, but I used to have other chapters also. On top of all these, we used to have other chapters. We used to have this thing called logic gates.
Yes, coding.
Oh yeah, transistors, right? Transistors and logic gates and all that. So we used to have a chapter on that, right? But it's now taken away because I think the government probably at some point thought that, you know, like, you know, we won't be IT based. I don't know. In the 1990s. Right, big mistake, right? You know what they thought you know what they thought we would be in Singapore? Like the big grand vision for Singapore in the early 2000s, like 25 years ago, like you know what was big grand vision? Bioscience, right? Like life sciences will be like the pharmaceutical hub. Okay, we built an entire big building at One North called Biopolis for the reason. You know, yeah. Then was it now? No, it's all dead now. Sorry, the pipe dream is lost. Right? IT was the big thing, right? But do we have like major IT campuses around? No, we don't. Right? We don't have any of that. But again, IT is also dying. So, oh well. There are just too many IT graduates nowadays. EMI, one of my favorite chapters. Because EMI talks about generating electricity. Yeah. So this thing works. I know this thing works. EMI is basically this thing that I'm holding now. So as I turn it, right, I'm generating electricity. Okay, so that's what this is. But you might not know this, but you know, I'm just telling you that there's so many other applications for EMI. Okay, one of which is your wireless charging. Right, when you put your phone on the base and then it starts charging, that's EMI. That means you can charge without wires. right? How does that work? You need to know also, right? I'll be teaching you that. Okay. Another one, Hai Di Lao. So when you go to Hai Di Lao, the induction cooker, right? Okay, when you go to those hot pot, right? There's a pot and then there's the induction cooker at the bottom. There's no flame. So how does it create heat, right? Also by electromagnetic induction. Yeah. Okay, but we'll deal with that later. Okay, so in this picture, right, how do you tell that this is not something to do with electromagnetism? So we've done electromagnetism, right? We've done electromagnetism, which we ended off with DC motor, right? So I'll do a bit of recap first before I go on. Right, let's do a quick recap before we go on. Let's see this. Okay, for EM, right, electromagnetism, we had a DC motor, DC motor. Can you recall the parts of a DC motor?
The split ring.
Split ring, carbon brushes, good, very good. So you had the magnets. Oh, excellent. You guys are like this is truly what you remember from my lessons because they haven't even done this in school yet, right? So thank you for that. But yeah, okay. So you had carbon brushes, you had the split rings, you have the wires, okay. And here's the thing: for a DC motor, right, one of the most important thing that you must have is you must have batteries, right? You gotta have batteries. No batteries, no DC motor. Okay, like, oh, maybe the contacts are not clean. I don't know. Damn it. Oh well. Okay, so you gotta have a battery like this. Okay, and this is under electromagnetism. This is in a very layman's way of describing to someone, right? You know, if let's say your uncle like during the family gathering asks you, hey, what you learn in physics, huh? Right? Then you tell them electromagnetism, then they ask you like, can you give a summary what it is? You just say that you're using electricity to create movement. Right? Isn't that what EM is all about? EM is all about using electricity to create movement. So what is EMI? Using movement to create electricity. Yeah, it's the exact opposite. So EMI is the opposite of EM, right? So you're learning this chapter, EMI. This is where we move things like this, right? And we generate electricity. You know what I'm saying? Right? You move it. Only when you move, then the bulb lights up, you see? You don't move, it won't light up, right? Okay. So look at this diagram. Look at this diagram. There's a magnet. There's a coil of wire. There's a bulb. The question is, how do you know that this is not DC motor, or how do you know that this is not EM? Rather, this is EMI. Like, what's the one thing that's not here that tells you that this is EMI? The battery. Yeah, the battery. The battery is not here. So nothing, there's no source. You look at it, there's no source of electricity. And what we're trying to do, we are trying to, right? We are trying to make the light bulb light up. Okay? Right? But there must be movement. There must be movement. There must be something moving. So on this diagram, please indicate that only when it moves, only when the battery moves, then the light bulb will light up. If the battery sorry, not battery. Only when the magnet moves, then the bulb will light up. If the magnet doesn't move, then the bulb won't light up. Okay. Okay, Ken. So on the next page, a very big blank page. I don't know why is it so big, right? I just want you to understand what is magnetic flux, right? So new word, right? Flux, right? Flux. Okay. Now in my lessons, I will say magnetic flux. Okay. When you write stuff down, depending on school, you could just write magnetic flux. But some teachers are very particular. They want you to write flux linkage. Okay, so you might have to write magnetic flux linkage. So in school, just pay attention to whether or not they're gonna ask you to write flux linkage. All right, just kind of like, oh, are you gonna make me write flux linkage? Okay. Okay, that's it. Let me show you what is flux. So we draw a magnet first. You don't have to draw so big. I'm just drawing it big for your own sake. Okay, so this is a magnet. So what do we have around a magnet? Right, we have magnetic field lines. Right, so this guy is gonna give off some magnetic field lines. Right, so you know it's like the aura around him. Okay, so this is a magnetic field lines. So I mean, magnetic field lines, you got to remember, you got to draw the arrows. Oh man, I was doing something halfway and then I totally forgot. Okay, never mind. I'll just finish this up first. So these are magnetic field lines, which is not really flux. Okay, so there's a common thing that, okay, so now the problem is this. Some teachers will just go ahead and tell you that, oh, flux is just magnetic field lines, right? They will just tell you it's the same thing. Okay, so now if you go on and do IB or JC physics, it's not the same thing. It's not exactly the same thing, okay? Right? So to be very clear, flux specifically are the field lines that if let's say, for example, I take a coil of wire, so I'm showing you a magnet here, sorry. This is a magnet. Okay, guys, you see this magnet here, right? This is a pretty strong magnet. There's a few neodymium magnets stacked up to each other. It's kind of strong. Hang on. Right? Yeah, it's quite hard to remove as well. Right? So it's a strong magnet. And then I put a coil of wire in front of it. Right? Like this, huh? Okay? So you can't see the field lines, okay? But you can kind of like visualize it coming out of the magnet. So usually I use this like my four fingers here to represent magnetic field lines. So the magnetic field lines are kind of like cutting through the area here, right? You see the area of the coil here, right? So the magnetic field lines are like poking through the area here like this. Okay, yeah. So what I want you to do is I want you to draw a coil here. Right? It doesn't have to be a nice coil. I mean, I just wanted you to make sure that you know there's a coil, right? It's a coil of wires, right? This coil is basically this coil. I'm showing you this coil here, like this, right? Okay, and I want you to kind of like shade one of the coil's areas by the side like that. Okay, so flux is the magnetic field lines. Flux is the magnetic field lines that is cutting the area of a conductor, right? Cutting the area of a conductor. So there you go. So we're not talking about cutting the wires. We're talking about cutting the area, right? The area here. So that's why I tried to make you all to shade this thing. So that's the true meaning of flux. But here's the thing, your teachers might just tell you that, oh, flux is just the field lines. Okay? Not quite right, but I'm just being specific here, right? Yeah. Okay. Now I realize that I have to do something very quickly. So can you give me like 1 minute while can you all just take the snacks and pass it around? So I just need to settle one thing. Hey, take the snacks and pass around. If you don't want, then just pass around. Okay, sorry, I am feeling a bit faint from not having lunch, so I'm just gonna go ahead and just eat and teach at the same time. Sorry. Okay, so that's flux, right? Hold on, my mouth is full. That's great. So read this thing here. Faraday's law tells us that the induced EMF, right, is proportional or directly proportional to the rate of change of magnetic flux. So layman's understanding is what? Layman's understanding is this: if you change the flux, you will get induced EMF, right? Like these two things are related, and they are. Magnetic flux is related to induced EMF. Sorry, the change of magnetic flux is related to induced EMF. So the idea is this: it must change, it must change. Okay? Then you can get induced. What is induced EMF? What is induced EMF, guys?
Is it like movement?
EMF? No.
It's from the
What? Voltage. Voltage. EMF is voltage. You're thinking of what? Electromotive force, is it? But it's just voltage. So the name EMF is a bit misleading because people will think there's something to do with motive and force. But it's actually just voltage. Specifically, we use the word EMF for what? Voltage of what? Voltage of a battery or voltage of a source. Good. Right? Voltage of a battery. Right? Okay? Or voltage of a source. You know what? This is not doing me. This is not doing anyone any favors. I'm just gonna finish my meal first before I continue. Right. So just give me another 1 more minute. Sorry. Okay. Sorry. I'm done. Okay. So you know what this means? It means that if you change the flux, you can create voltage. Okay? Right? So that's what Faraday's law says. I think the big question is this: so how do you change the flux? Right. Let's go back to this diagram here. Like if this diagram shows you flux, field lines cutting through an area, how can you try to change the flux? Right, so I'll use these fingers again to represent the field lines, and this is the coil, and that. So how could you change it? You could push a magnet towards it. If you push it towards it, there's an increase in flux. That's a change, right? How about pulling it away? If it was near and I pull it away, is that a change also? That's also a change. That's also okay. In fact, that will also create electricity. So sometimes some students will be like, hey, if you pull it away, isn't it like you removing it? Right? Okay. Any other ways?
Is there a unit
For flux? There's a unit, but it's not in the syllabus, don't worry. But it's Weber. Yeah. WEBER, but don't worry about it. Okay? Any other ways to change it? You could literally just move the coil instead of moving the magnet. You could also move the coil up and down. You can also move it left and right. Right? You can also move the magnet left and right. You can move the magnet up and down. That's also fine. You could also flip the coil. You could rotate the coil. So if you start rotating the coil, right? If you start rotating the coil, then you're doing this. You're rotating the coil already. You know? Or you could also rotate the magnet. So you could start rotating the magnet, and the magnet is like, you know, flipping like this. So as long as there's a change, as long as there's either increase or decrease, okay? But let me ask you this, okay? Let me ask you this, though. Right, look at this, huh? Okay? So there's flux, correct? There's flux. But if I hold it there and don't move, is there a change? No change, right? So if I don't move, there's flux, but there's no change, so is there induced EMF? Don't have, there must be a change, right? I keep emphasizing that. Okay, good. So you all understand. If there is flux, but it doesn't change, there is no induced EMF. How about if I do this? Like, look at this, huh? Look at the coil. Look at the coil. What happens if I rotate it like that?
the area is still the same, so it wouldn't change.
Correct, it doesn't change, right? So that's also trying to show you that there's no change. So you got to be aware that sometimes there's no change, even though you move it, okay? So, or you move the coil like that. Sorry, if you move the magnet like this, then there's also no change. Correct? Yeah? How about if you move the coil and the magnet together like that? Then there's also no change. So not all, it doesn't mean that if you move, there will always be a change. So sometimes some movements do not give you a change. Okay, so if you understand that, that's fine, right? We don't have to worry about it. Okay, so we're gonna just draw this according to this thing here, right? According to this thing here. If you move the magnet towards a coil, there's no battery, right? And what happens if you put a lamp, right? A lamp here, like this. This is a lamp. Okay, this is a lamp here, like that. Okay, and you move the magnet towards the coil. You move the magnet towards the coil, right? The lamp will light up, right? So as long as you move, right, the lamp will light up. You understand? Okay. So whenever you do, like, you know, these EMI chapters, there's actually always 4 steps of describing how the thing happens, right? I'll go, like, the first 2 steps are basically this. If you move the magnet, number 1, if you move the magnet, there is a change of flux. There's a change of magnetic flux. So we say that there's a change of flux. Okay, but strictly speaking, there's only 2 objects here, the magnet and the coil. Which one is experiencing the change of flux? The coil. The coil. I just want to make sure, because you know why? Some students will write, oh, the magnet experiences a change of flux. Right? That's wrong, right? Okay, so the coil, right? There's a change of flux in the coil, right? So I will write it like that. Like this, the phrasing is like this: change of flux in the coil. Okay. Number 2, based on Faraday's law. Based on Faraday's law. Now I'm shorthanding this because I don't want to write the whole statement down, right? It take me too long. Based on Faraday's law, what happens to the coil? The coil experiences what? Or what does the coil get? Coil gets good induced EMF, right? It gets induced EMF. You get what I'm saying, right? Okay. Now this is me, This next part here, I'm going to write something here. This is me. You will not see it in school. Okay, I like to write it like that. Induced EMF. I like to write a little I in front of it. to show you that that's an induced thing. Okay, it's like iPhone, right? You get it, right? So IE. So that's the induced EMF. So anything that's induced in this chapter, I like to put a little I to it. But the thing is this, it does not appear in any one syllabus at all, right? It's just a me thing only. It's like, that's the way I like to teach it. Okay, so induced EMF. So do you understand that the coil becomes a battery? Yeah, the coil literally becomes a battery. You know what I'm saying? Right, the coil becomes a battery, and therefore the coil will now supply electricity to the bulb. And that's why the bulb will light up. Okay? Right. And you have just finished like half of the most complicated things in this chapter. Like literally the half of the most complicated thing is this Faraday's law. Right? Like students always forget about this word. Like that this is the word that they always forget. It's the change that causes the induced EMF. Okay? Your job is to always eyeball and see, is there a change here? Is there a change there? Is there something that's causing a change here or there? Or anything like that. Okay? So yeah. Now the next one will be the second half, and that will be Lenz's law, right? Lenz's law. Okay? Lenz's law is also one very lengthy thing, but Lenz's law basically just helps you, like the most important thing for Lenz's law is it helps you tell the direction. It helps you to tell the direction. Okay, we know that the coil becomes a induced battery. We know that there's induced electricity here. We know that there's induced voltage here, right? Current will flow into the bulb and make the bulb light up. The question is, how does the current flow, right? Technically speaking, it's a wire, right? The current can only flow either up the wire or down the wire. You know what I mean, right? So yeah, we're going to use Lenz's law to figure out where's the direction of the current. Like, is it flowing a certain downwards or is it flowing upwards? Like, how do we tell? Okay, so for Lenz's law, the key word is oppose. The key word is oppose, right? Essentially, what Lenz's law is trying to say is that if you do get an induced current in this coil, the current's direction will be such that it will try to oppose whatever you're trying to do to it. Okay, right? So it will try to oppose the change in magnetic flux. So you see, we had the change in magnetic flux above. Now Lenz's law tells us that the coil will try to oppose it. It's like, oh, right, what are you doing to me? I want to do the exact opposite of what you're trying to do to me. Okay? But please take note, oppose does not mean repel. Right? This is also another common mistake students just kind of like simplify in their head. They think that, oh, oppose means repel. Or oppose just means opposite pole, which is also wrong. Like what does it mean to oppose? It's like it's not even about like, you know, a certain pole or a certain force like repulsion, or like it's always north pole versus north pole or anything like that. Oppose just means to rebel. You understand? Are you all, yeah, resist lah, right? Resist, okay? Kind of like do the exact opposite of what you are trying to do to it. So give you an idea here, huh? I am trying to push the north pole towards the coil. Okay, I'm trying to push the north pole towards the coil. What will the coil try to do to oppose that? What? So the coil can't move, right? The coil can't move, but what it can do is that it can induce electricity inside. So it can induce electricity inside, and then so specifically is a coil. Do you remember what coils are for in electromagnetism? Coils, not soft iron. Like, I'm not talking about the bar, I'm talking about the coil. Not the core, sorry, the coil. Yeah. Like, do you remember what are coils when you have electricity running through it? It becomes a electromagnet. It becomes an electromagnet. Okay? So here's the thing, so this coil will become an electromagnet. That means it will have a north and south pole. Alright? So what would it try to do? It will induce a north pole on this side. Right? Yeah, you're right. Okay? So based on Lenz's law, we understand that the coil will try to induce a north pole on that side, because if you're pushing the north pole towards, the coil will be like, no, go away, right? So I will try to induce a north pole to try to push you away. Okay, but please take note, it is not the repulsion that's the opposition, right? It is basically you bring a north pole towards me, I induce a north pole to resist you. Then you use your right hand grip rule. Since it's a coil, and we know that the induced north pole is on this side, we use the right hand grip rule, right? We do the right hand grip rule, then we understand, oh, the induced current is going to flow this way, right? Inside. So I'll label it as II, right? So that's to indicate that there's an induced currents, right? Trace the current through the bulb, right? So trace current all the way through the bulb. You realize that the current flows like this. Okay, so step three is to recognize that, you know, basically, right, based on Lenz's law, right, based on Lenz's law, induced current is in a direction that opposes what again? Yeah, the change in flux. Okay, so induced current is in a direction that will oppose or that opposes the change in flux, and you realize that, hey, that's like you going back all the way to the top again. Okay, right? Now, in most cases, in almost all questions that you do for this chapter, like I said again, this chapter has no equations, just like the previous one. It's all diagrams. It's all this hand rule, that hand rule, this hand rule. It's all concepts. Okay, it's all perspectives. So you got to learn how to write this. Like you literally, most of the questions that comes out for this chapter, right, is you have to write 1, 2, 3. There's a fourth point. Okay, point 4 is to ask you to check for opposing force. Right? Check the direction of opposing force. Okay, check the direction of the opposing force. So in this case here, I want you to kind of like imagine, right? Imagine you were the one who's trying to push it, right? You would have applied a pushing force, right? I will apply a pushing force, right? I will apply a pushing force like this. But as I push this magnet towards this coil, and as the coil gets its induced EMF, induced current flows, it induces its own north pole, will I experience an opposing force here on the magnet? I will, right? I mean, it's repulsion, right? Yes, it's repulsion. So in a way, the understanding is that there will be some sort of like opposing force. Okay? Opposing force. Yes, right, Kayu, you're right. You can actually say that there is an opposing force acting on this magnet. So kind of like that's why, so on the coil. That's why the coil will move away. But it doesn't actively pick up, and then move, right? But it's actually being repelled. Okay? But if I were to fix this coil on the table, then this coil can't move. So we can't say that it move away, but it will experience a repulsion force, right? Like, it causes its own repulsion force on itself. Right? It's like these two forces is North Pole versus North Pole, right? Yeah, there we go. But let's focus on this. Let's focus on this guy here. Let's understand this one here. Now, today's lesson is like feels very slow paced, not on intention. If I were to go any faster, right, you guys will miss a lot of points. So that's why I need to be like a bit slower and a bit more detailed, okay? Right. So imagine what this guy is experiencing as he's pushing. Yeah, he's gonna experience some resistance, right? So I'm gonna pass this thing around, right? The idea is here is this, right? As you're pushing the magnet, it's kind of like you're rotating this thing. I want you to get a feel of like how it feels like to rotate, and you realize that like the rotation is not very smooth. Okay, so try kind of like rotating it and kind of feeling it, right? So the idea here is this guy, right? Like what she's trying to do, and she'll pass it over to you guys as well, right? That when you push, you will feel like, there's some sort of like resistance to it. Yeah, you can. Yeah, you see, right? Yeah, you can do it either way. But either way, also you feel that there's some sort of like resistance, right? Okay, so what happens also is some students mistake this for friction. Some students will start saying that, oh, it's friction, but it's not friction. The reason why you feel like it's a little bit hard to rotate is because you are trying to generate electricity simply by just overcoming the opposing force. Okay? Okay, yeah, you try it first.
We used to have one of this, like, smaller version.
Exact same model.
No, no, no.
Oh,
It was like,
okay, that one was from the NDP pack.
no, it was something else.
Oh, something else? Okay, yeah. This one from IKEA.
Yeah, it's
Yeah, it's so annoying cause like at first when I saw it on the shelf, I'll be like, what a god ugly looking like pepper grinder. You know? Right? Then afterwards I saw someone holding it and doing this. Then I was like, why it got light one? I thought it's like one of those like pepper grinder that has a lamp. Nowadays they have, right? Okay. Then afterwards I pick it up and realize, hey shit, it's a hand powered torch. It's like literally a hand powered torch, you know? Okay. Yeah, so a bit misleading because this hand power torch, the insides has a rechargeable battery. So kind of like the more you turn, right, the rechargeable. So it's supposed to go completely off, but it looks like it's quite like a little bit on, right? So just imagine that it's like not working, right? I have to find a way to. Okay, I don't want to break it. I know, and this one already broken. I don't want to break this thing. Okay, but anyway, so if I don't turn it, it's not on, Okay. But yeah, can so am I also right to am I right to kind of like help you understand that this guy kind of like has to do work against the opposing force. Like he has to do some work against opposing force, right? Like you know, if I want to rotate this thing, I have to push a little bit harder. Right? I have to push a little bit harder. I need to, you know, overcome that the opposing force. Okay? Okay, and this is the important part. This opposing force is due to what? I think it's based on what? This opposing force is based on Lenz's law, right? So Lenz's law is known to be an application of the conservation of energy law. Okay, right. So explain why Lenz's law is a conservation, an application of conservation energy law. So what am I doing? I'm doing work against the opposing force, right? Okay. What kind of work is that? What kind of energy is that? Me doing work against it. Like that will be mechanical energy, right? Right, mechanical energy. So it's a okay. Actually, that's not a very good thing, right? To say mechanical energy, that's bad. What is it? That's kinetic store, right? That's kinetic store because we have to use the new syllabus, right? Yeah, kinetic store. That's so annoying. Kinetic store. Okay. So I'm uh, chemical potential energy store, right? Chemical potential store, right? And then I'm converting it into kinetic store, right? To move the thing, and then you know the kinetic store is converted into light, right? Electrical energy. So work done against opposing force is converted into electrical energy. This statement here is talking about the conservation of energy. So if they ask you, explain why Lenz's law is an application of conservation of energy, then your answer is, oh, because as the guy is moving the magnet, he'll experience an opposing force. So when he does work against the opposing force, his work done is converted into electrical energy, right? That's the reason why, right? Energy is conserved. Okay? Okay. Now, unfortunately, I need you to do this on blank paper, right? The next thing. Yeah, we're gonna do some separate scenarios now. Okay. So, draw the setup. Okay, we're gonna draw the setup. Same setup. So we draw the north pole, we draw the south pole. Okay, and then we draw the coil. Right, draw the coil. So just be very careful on how you draw the coil. I want you to draw it exactly the same way that it's coiled as in my notes. So I think, the way I coiled it in my notes was a elongated S, or you can think of it as an integral sign, right? Not the flip one, right? So it's like a letter S, right? Like this. And then you connect it to a bulb. So this time now, instead of pushing the magnet in, I'm going to pull the magnet away. So I want you to imagine that you're pulling the magnet away like this, pulling it away. Okay, so move, right? We're trying to move the magnet towards the left. Okay, so tell me what happens. Hey.
If it moves away, is it
Uh-huh.
like induced sound?
You're saying there is an induced sound there? Induced sound? Why would you say that?
Because if it's wants to move away, it opposes motion, so it will follow it. I mean, like
You try to attract it back, right? So it's kind of like, okay, so if anything, right, just kind of always put yourself like this is you, for example. You're like the coil, okay? You're like the coil. So if the north pole is going away, you'll be like, hey, where are you going? Come back, right? So I would try to induce the south pole to try to attract it backwards, okay? So that's how you determine what's the direction of the thing. And then how do you determine the direction of current? Okay, do it. So induced current now will be, wrong color, sorry. Like this. Okay, induced current. And then you realize that the current, look at the bulb. Just now the current was going from right to left. Now it's going from left to right. So guys, what happens if you continue to push the magnet in and out and in and out? What do you get? AC. You get alternating current. This is the origin of AC. Right, so you get your alternating current. So your current will kind of like look like this on the graph. Let's just draw the graph. Right, current time graph, the induced current time graph will look like this. Okay, the idea here is that it's positive and it's negative, right? You got positive, negative means that it's alternating, means it's changing direction. So only if you continue to move this magnet, if you stop at any point, right, there's no current. Okay, couple other things, right? I just want to make sure that you get the idea for all of this. Is there an opposing force? Yeah, there is. Where's the direction of the opposing force on the magnet? Yeah, it's pointing that way, right? So as I'm pulling it, right, you can say that my pulling force is this way, right? My pulling force is pointed this way. The pulling force, okay, my pulling force pointed that way, and then you can say that, oh, the opposing force will be pointed that way. So what you also do notice is, right? What you also do notice is, like usually the person who exerts the force, right? The pull or the push, I always draw an arrow that's a little bit bigger than the opposing force, right? This is just to show you that eventually this magnet can move, and the opposing force cannot be bigger than the force there, right? Yeah, how can the opposing force be bigger, right? So you have to remember that the opposing force was created by what? The opposing force was created by the induced current. The induced current is created by the induced EMF. The induced EMF is created by the change in flux. And the reason why there's a change in flux is because this guy is changing the flux, right? So he's in a way, right? It sounds like he's doing the very thing against himself. Like he's the one who's trying to create the current, and the current will act against him. But that's how electricity is generated, right? That's how it works. Okay, yeah. Can I? Okay. Then the next thing is this, right? I just want to make sure that you understand. How does is that possible? Can a bulb work on an AC? Like let's say you have a bulb and then the current's flowing left and right, left to right, right to left, left to right, right to left. Why would the bulb light up on both directions? Yeah, the answer is yes, huh? Yeah, the answer is yes. Let's think about a bulb. What's inside the bulb? Filament. You're right. What's it made of? What's a filament made of? Tungsten is just a metal, right? So let me just like do a little bit of a deep dive into the filament. So we have the filament like this, right? So maybe right, this is a filament, right? I want you to imagine that you're an electron inside here like this. Okay? I want to imagine there's an electron here like this. And it's an alternating current. That means if the guy keeps pushing and pulling the current, pushing and pulling the magnet here like this, the current wouldn't it move like back and forth? Like it will just keep on moving back and forth, back and forth, back and forth. Imagine the electron. What are you doing? What's happening to you? What? No, yeah, that's the word oscillating, or you can say vibrating also, right? So literally the electron is gonna like whoa, okay, whoa, like hey, then he goes back and forth, back and forth, back and forth. Like then what he gonna do? What does the electron do when he does that back and forth thing? What does he do when he does the back and forth thing? He's colliding into the atoms, right? He's colliding into the atoms. These are all the atoms, right? And when he collides in the atoms, right? He's moving back and forth. He's colliding, 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 colliding. What happens to the atoms? What do they do? Yeah, they start to vibrate more vigorously. Not just they start to vibrate, they start to vibrate more vigorously. So because of the increased oscillation of the electrons, the atoms vibrate more vigorously. Right? So what does it mean by the atoms vibrating more vigorously? What will happen? Generate heat and light. That's basically how heat and light is generated. That's how a filament produces light. Okay? Right? Yes. Okay. So this vibration would emit heat and light. Okay? So this is the vibration and it will emit heat and light. Okay, so yeah lah. So agree or not? Filament lamps can work on AC. It's fine because the electrons are just bouncing back and forth. It's making the atoms do what they're supposed to do. They're supposed to vibrate more vigorously. They're supposed to vibrate so that they can emit the heat and light. If it wasn't AC, what was it? Yeah, direct current, right? DC, right? It had just been a battery, right? The idea is the same. The electrons are just flowing in one direction, but at the same time, just colliding into everything. Okay? So if it was a DC circuit, it was a DC circuit like this, right? The idea is that the electrons are still like doing its thing. The electrons are still right, just oh sorry, wrong direction. Right, the electrons are just kind of like just bashing through all the atoms there, causing the bulb to light up lah. Okay, yeah. So what is really what's the difference between DC and AC? AC, the direction changes, it goes from plus to minus, minus to plus. DC, the direction doesn't change. That means if it's flowing this way, if the current is flowing this way, okay, the current is forever flowing the same direction. Direction, it doesn't mean about the magnitude. So you could make the DC increase, decrease, increase, decrease. So it goes up, it goes down, it goes up, it goes down. But as long as it's always in the same direction, it's still considered DC. No, it doesn't matter. Yeah, it could be you could start from anywhere. So in math, right, you got your sine, then you could also start from cosine, or you could start from negative cosine, or you could start from negative sine, right? So yeah, or you could even start from somewhere in between. Yeah. Okay, this can okay, good. So this is like kind of like to showcase to you what's all this induced EMF, all this all about, right? AC, right? Is AC dangerous, that sort of thing. Right. So if you go and read up the backstory of Thomas Edison and Nikola Tesla. Nikola Tesla was the one who kind of like invented AC, right? Alternating current. And Edison was going around showing the rest of America how dangerous AC was. Yeah. You know what some of the weirdest shit he did? He went to go and electrocute a cow or a dog or something like that, like using Nikola Tesla's like AC current. Like he was trying to show like and he zapped this poor animal with AC current and saying that oh AC is really dangerous, that sort of thing. Dudes, AC, DC both are equally dangerous, right? High enough voltage, high enough current will kill you. Okay, so
Because it's like, well, the bulb will like right now when it's minus. Okay? Like resistance will cause. So when you keep like resistance.
okay, so it's okay. Resistance is a contradictory thing. Okay, you increase resistance, P equals to I squared R. Okay, then you'll be thinking, oh, doesn't that cause the power to increase? Wouldn't that be brighter? Because more resistance will cause more heat, right? But at the same time, you also got to remember that resistance will also cause I to drop. So when you do P equals I squared R, like how? So it depends on what you're trying to keep constant. If let's say you have one battery, 6 volts, okay, and then you have a bulb. Let's say the bulb is like 6 ohms. Then it's a certain brightness, right? Then you swap out that one for a 12 ohm bulb, and then you compare. So 6 ohms, 12 ohms, but the same 6 volts. Like which one will have a higher, like a higher, a brighter, which one will be a brighter bulb? The 6 ohms, right? Why? Why? Which equation are you thinking of? You should be thinking of P equals to V squared over R. Because if you're keeping the same voltage, then V is constant, right? Then you're just looking for the lesser R. So the 6 ohms bulb will be brighter, right? Yeah. But if let's say I change something else, let's say I change the bulb, let's say I change the battery, then that's a different issue altogether, right? So don't don't just imagine things, okay? Do the questions if you need to. Okay, wait, hang on. I want to talk about this. Okay, so here's the thing. But there is one special feature of AC currents. There is one special feature of AC currents, which is this, right? So I'm gonna just tell you this, Notice this, When it's going a certain direction, it's positive. When it needs to reverse, it will go the other direction. It becomes negative. But in between, what happens to the current?
Zero.
Zero. Does that mean that this bulb will flicker? That means will the bulb like, right? So you see me do that video before, right?
You said
I sent it. Yes, I sent. No, I sent it in waves. I sent it in DC circuits. I sent it just 2 days ago, right? In the group chat. So if you look at the group chat, it's there, right? There was this video I sent out, right? This, right? So that was this that was this lamp up here, right? That one up there. Then there's another one up there also. Okay, and essentially it's flickering, right? It's flickering, uh, but only when you use a slow motion video you can see it. Otherwise, I look at it, we can't see it, right? Because the flicker is about 60 hertz, right? Our power supply is 60 hertz, right? So our eyes can't see anything beyond 30 hertz. So to us, it looks like a continuous stream of light. But when you use a digital camera, right, it will show you that, oh, it's actually going back and forth. So same thing here as well, right? So the idea here is if I do this very slowly, right, if I turn this very slowly, right, you can see that it also flickers. So it goes bright, dark, and bright, dark, and bright, dark. Right, I try to keep it a constant rotation. Yeah, because as you turn, it's alternating current, and if it's an alternating current, it needs to switch direction at some point, and at some point it's zero. So it will flicker, but obviously we can't see it. Okay, right? So there you go. Okay, this concept done. Let's work out another concept. Same diagram. Same diagram. You all need a quick break? I got half an hour more. You need to go toilet, drink water, eat snacks. Snacks? No, you're not taking snacks. What? Why? You'll just put the snacks aside. What? But I can understand if one of like one of my other classes they don't like snacks because one of them is allergic to chocolate. I'm like, what? That's the most horrible thing to happen. I feel so sad for him. Allergic to chocolate? What? Okay, anyway, so okay, north, south, same setup, everything same, okay? Everything same. Coils, everything same, right? But not bulb, voltmeter. I'm gonna put a voltmeter, right? And dude is trying to move the magnet again. Okay, so the thing is this, right? Describe what will happen to the voltmeter when the guy is pushing the magnet into the into it.
You said that earlier that the solenoid becomes electromagnet. So would it be
Don't jump to the end. Start from beginning again. Right? You push the magnet in. Is there a change in flux? Is there induced EMF? What will happen to the voltmeter? I'm asking you about voltmeter. What does voltmeter measure? Voltage. So if you got induced EMF, will the voltmeter give you a deflection? Yeah, there will be lah. So yes, there will be a deflection. Right? The voltmeter will deflect. Okay? Understand? But is there induced current? Think carefully, Look carefully. Is there induced current?
just an infinite resistance?
The voltmeter is like sitting right there, smack in the middle of the circuit, right? Right? He's locking up the whole road, right? No induced current. Why? Because the voltmeter is there, right? The voltmeter has infinite resistance. So what's the implication? The implication is you still get a voltmeter reading because the EMF is registered, the voltage is registered, but there is no induced current. So if there's no induced current, does it become an electromagnet? That's why I say start from beginning. So this is no longer induced electromagnet because there's no current flowing through it. So is there an opposing force? No opposing force. Okay? Wait. Hang on, wait. I didn't catch what you just said. Try what? Why? Go on. I heard you say what you said, but yeah. So zero resistance, then you get induced EMF, then you get induced current, right? Hey, you're not wrong. it might be dangerous. But here's the thing. So in a way, right, like the danger is mitigated because you're pushing the magnet, right? Like if you stop pushing, what will happen? Then there's no more induced EMF lah. But you're right. If let's say you're talking about a big magnet and a big coil, many coils, right? And then you push it one time and you have an ammeter, you could actually create a very large current that could burn stuff. Yeah. But I mean, it's like, but as long as you can continue pushing it, if you cannot continue pushing it, then it won't generate lah. It's not like a battery. If let's say I literally put a battery to a ammeter like this, then yeah, something will burn, right? You've seen those survival skills things? You know, they take an aluminum foil, right? They take aluminum foil, they cut it into this shape, like this, a very thin bridge in the middle like that, right? Then they connect it to the ends of a battery, like they put it to the ends of the battery. Then the middle part actually glows red hot. Yeah, yeah, it actually can start burning stuff. Like if they use it to start fires that way. Yeah, yeah. Anyway, so okay, so we're done with this concept. Let me go through the next thing. Right, so can you all flip to the next page? Yeah, flip to the next page here. This one here. We're gonna go through this one here. Okay, so very quickly, I'm gonna drop a magnet. This time around, I'm not pushing or pulling. I'm just gonna let it drop. I let it drop through. Right, let it drop through this coil of wires that's connected to this thing. This thing here is a galvanometer. Right, it's a galvanometer. So anyone tell me what's a galvanometer? Galvanometer. We know we done a voltmeter, we done an ammeter. What's a galvanometer? Is that what? Sorry, what? Galvanometer? It's a very sensitive ammeter. It's an ammeter. It's a very sensitive ammeter because it's used to measure what? It's used to measure small amounts of current. Okay, so it's a very sensitive ammeter. Okay, yeah, there you go. So how about this? How about we go through this? Okay, as the magnet is falling, right? I think I've gone through in much detail for you to apply now. As this magnet is falling, the north pole is approaching the coil. What would the coil try to do? It will try to induce a north pole at the top. Correct? Yeah, okay. You guys are getting it, right? You guys are like understanding this now. So it will try to induce a north pole like this, induce a north pole. So how does the current flow as the magnet is falling towards? Yeah, good. Correct, right? You do the right hand grip rule. Seems a bit weird though. You should grip it towards you. Like if you're sitting there, you should grip it towards you like this. Like your fingers must face you. Because like that's the front of the coil. Right? So it's facing you, right? Ah, good, correct. Okay, good. So then the induced current will be like flowing this way, right? Okay, so this is the induced current. Okay, induced current. Then the magnet will fall. This time around, it's falling through. So the idea here is it's falling through. Is a solenoid is falling through the hole, right? So the other class, some of them had a trouble trying to understand this, right? But this block here is the toilet roll. It's just kind of like this, and I'm dropping the magnet through the hole in the middle like that. So it's fall through the middle, and it comes out like that. Can you understand this? Huh? Yeah. Okay. So once it starts falling away, notice that the south pole is now leaving. Yeah, the south pole is leaving. So what will the coil try to do? On the bottom, right? So as once the magnet has fallen through and then past the halfway mark, and then as it's going away, the coil will be like, hey, dude, don't go away, right? So they'll try to induce a north pole at the bottom. And if it induces a north pole at the bottom, then where will be the direction of the current? Yeah, like it's the other way. Correct. So right grip rule this way, like that. Okay? Right. So like this. Okay, it's one thing about the current, it's another thing. All right. So the question is, what happens to the magnet? Like, is there anything that happens to the magnet? Okay, anything special that happens to the magnet? Does it experience the opposing force? Yeah, it experiences the opposing force, right? So you will be able to see that that the magnet falls because of its weight, right? Mg. But as it's falling towards, there will be an opposing force. right? There'll be opposing force, right? There'll be opposing force. And if it continues falling after it falls out, the opposing force will then be acting upwards. That's an opposing force. So I want you to kind of like, before I show it to you, kind of like think about like, how do you think it will look like? Like, how do you think this magnet will be falling? I mean, compared to something that's just free falling, like just a magnet that like that here, right? And then it just like, what will be the rate of falling of this magnet? What? Huh? Which one is slower? This one will be slower, right? Because this one will be free falling, right? But what's the acceleration of free fall? 10 or 9.1. Okay, fine. Right, so A is 10 meters per second squared, right? You all better write your 9.81 there, right? But then this one, how about the acceleration of this guy? This guy's acceleration will be less than 10. Okay, less than 10 meters per second squared. Right? Yeah. So it'll be less than 10. So as a demo, I'll show it to you now. So what I have here is a small magnet. What I have here is a copper tube. It's a brass tube, right? Copper tube. Okay, and I'm gonna drop this magnet through the middle here like this, right? So we're gonna drop it through the middle. So kind of like, you probably can't see the inside of it, but I'll just show you that I'm gonna try to catch it, right? So hang on, right? So it takes a kind of like a longer time, right, for it to travel through the thing. And that's basically what's happening to the magnet as it's falling, right? So there's an opposing force. In fact, you might be thinking, wow, the opposing force is, doesn't it feel like quite strong? Right? Yeah, it does feel like quite strong. Okay. Now, what happens is that a lot of students don't understand this part, because this is the part where they're, oh, does this mean that there's an induced current in this tube? Like, does the induced current flow around the tube? And the answer is yes. So even though I'm holding it, and even though there's an induced current, it's not very strong. But if I were to put like a galvanometer onto this tube, right, or maybe some electrical meter or something like that, it will actually detect some current as I'm dropping this magnet through like this, right? There'll be some current, just that, yeah, there you go. Can, right? If you want to take a look at it, you can. Try to keep the magnet away from your phones, because it's quite a strong magnet. That's a small one. Like, this one, definitely don't let it touch your phone. This thing will mess your phone up. Yeah. Okay. Yeah. Cool, right? Yeah. Electromagnetic induction science. Okay. Once you play with that, we will start drawing the last concept for today. And once you start drawing the last concept for today, I will continue this next week. Yeah. Yeah. Right. Yeah. It's actually quite slow. It's quite weird. Yeah, just put it on the piece of paper. That's fine. I'll come and get it later. But yeah, so that the thing is that tube is copper. It's a brass tube. You get what I'm saying? So like, brass and copper has no magnetic properties, right? So this is, I mean, I'll just call it copper, right? So copper is non-magnetic, right? You can't attract it like this. You know what I'm saying? Like, you can't attract it. But once you induce a current in it, then it will become an electromagnet. So as the magnet is falling, this tube is a temporary electromagnet, because it's doing that in, like, the induced current this way, and it becomes a magnet that opposes the magnet's field. So for that moment, while the magnet is falling through, this tube becomes an electromagnet, but it itself is not magnetic. Yeah, copper is not magnetic at all. Okay, there you go. Yeah. So the next thing I want you to draw will be this. So usually some schools, especially the IP ones, right? You will get this in your, either your schoolwork or your test or something like that. And then some students get like visibly confused about this. So I'm just gonna go through this very quickly. Okay? Right? It's similar to that concept in my notes. It's similar to this, right? It's similar to that copper tube. Okay, but the difference is this is only one coil, one single coil, one very thin coil like this. Okay, one coil, and it's connected to a voltmeter to check its voltage. Okay, one coil. So I'm trying to do one coil here. No, that's a different diagram. Yeah, that one is a little bit different. So this one you draw your own. You draw your own. You find maybe on the page before or something, or maybe you just draw at the bottom left corner space there. Yeah, you don't need such a big one, right? It's just it's this diagram plus a graph, okay, plus a small graph, okay. So I'm gonna drop the magnet through, right? I'm gonna drop the magnet through. So once it drops through, right? Once it drops through like this, then your understanding is that then there'll be a deflection in the voltmeter lah, right? Okay. But here's the thing, because it's one coil, the opposing force is negligible, right? Because it's only one coil, right? It's so small, right? Then what will happen is that the magnet will just fall straight through. Okay, it wouldn't slow down like that, like the case there, right? Like the one in my notes or in the demo that I'm showing you. Okay, so what is the acceleration of this thing here? 10 meters per second squared, right? So like it will accelerate lah, you'll get faster and faster. Okay. So because of that, because of this particular question, if you do see it, right, if you do see one coil with a voltmeter, right, you are very likely to be given a graph of the voltage time that's induced inside the voltmeter, inside the coil, sorry, and the voltmeter is recording it. Okay, and the graph will look like this. Oh, sorry, wait. Okay, there's a few nuances that I want you to pay attention to. The first peak that you draw, right, is not so high, okay, but it's very broad. Then in the second half of what you're drawing, the peak is very like no like low, right? It's indicating there's a very high induced EMF in the negative direction, right? But it's not so broad, it's a bit narrower. Right? Then I want you to label T1 and T2. Okay, couple of questions. Why is T1, or rather, why is T2 shorter than T1? Oh, you know what? What does this point in the middle represent? Any wild guess? The moment it passes like the halfway mark, right? Yeah, exactly. Yes, right. So as the magnet falls through, right, as it falls through, like exactly at the halfway mark, that's like the turning point, right? Okay, good. So back to my first question. So why is T2 shorter than T1? So it's like T1 will be the time taken for the magnet to fall towards, but then yet T2 will be the time taken for the magnet to fall away. So T1 will take this amount of time, and then T2 will be a shorter amount of time. Why? Yeah, because it's accelerating, right? It's accelerating, so T2 is shorter lah. it gets faster, right? For the same distance above and below, right? T2 will be shorter because it takes, it's getting faster and faster. So, yeah, that makes sense. Okay, so with that, explain why the induced EMF is greater on the second half. Because the induced EMF at the first part is like yay much, but then when it's on the second half, after it's fallen through halfway, wow, it's like a lot more induced EMF. Like, why? There's no opposing force. So you have to go back to basics again, right? Induced EMF is caused by what? Specifically, not just change in flux, the magnitude. Okay, read the statement again. Faraday's law says that what magnitude of induced EMF is directly proportional to rate of change of flux. So yes, okay, right. What I'm doing is I'm just giving you another level up, right? So our understanding is yes, you get induced EMF when there's a change in flux, but not only that, the amount of induced EMF you get is dependent on how fast it's changing. There you go, right? So in the second half, right, rate of change of flux is greater. Therefore, the induced EMF is greater. Okay? And I don't know whether you remember this, but in physics, right? In physics, whenever we say something is greater or lesser, right? When we say something is lesser, it's going towards zero, right? The minimum is zero. So don't confuse that. This is not the minimum, This is not minimum. This is basically very high voltage, but in the opposite direction. Okay. So last question is, why is this positive? Why is that negative? Well, not bad actually. Okay, so what happens is, right? No, you're not wrong. So what I want you to learn is this, The reason why is positive and negative. Okay, so some of the students they will say this wrongly. They'll say that this is due to Lenz's law, but technically speaking, this one positive, this one negative is not really due to Lenz's law, right? It's due to how the change is happening. So let me show you this, Okay, as it's falling towards, as the magnet is falling towards, what's the kind of change? Like, what does the coil experience? It experiences, like, specifically, what's the change? It gets more flux. Like, do you agree that, as it's falling, the flux increases? Flux increases. What happens when it's falling away? Flux decreases, right? Flux decreases. So as it's falling towards the coil, right, the magnet experiences more flux. It's a change. So in a way, if we draw this to be positive, right, then there's the sign of the voltage that was created inside the coil, right, as it's falling towards. Then as the magnet falls away, right, the amount of flux gets less. It's also a change, but it's a change in the opposite direction. So therefore, like, therefore it becomes negative. You understand? You what? I mean, it's just that it's just basically increase and decrease. So, like, based on the type of change, it gives you the direction of the EMF. Yeah. right? So different change, different types of change, different direction of EMF. Oh, I mean, maybe you might be thinking of, could you have drawn it the other way around? Like, what if I drew the graph this way? Can? Is it possible? Yeah, absolutely. As long as it's the opposite direction, right? As long as the opposite direction. So as long as the first half is the opposite direction of the second half, it makes sense, right? I mean, what can't you do? Like, what can't you do? You cannot draw it like that, okay? You cannot draw it like this, then like that. That'll be wrong, lah. Okay, because then that means you're saying that both sides the type of change is the same, right? Yeah, so that'll be wrong. Okay, I'll keep the rest for next week, right? Because this topic is like that. This topic is a bit mind-boggling sometimes. Meanwhile, while you're doing the things in school, please just, I know you're on magnetism, you're on practical electricity. Whatever the teacher says in school, right? If you like not sure or you kind of like doubt what he's saying, you just let me know, right? I'll answer you on WhatsApp. Okay? So yeah. Uh, what's the next test schedule? Oh, that's it. When is it? Physics is when? Oh, one of the last ones. Okay. You? What the heck is that? What's that? Oh, that's EOI. Same thing. Okay, good. So you all will end by, you basically will end by October. Start of October. That means I will not see you for the most of October, November, and December. Like, bye bye. Yeah. Last time I used to be at this tuition center whereby even year fours, right, they'll still make the students come back for lessons on October, November, December. I'm like, oh gosh, what am I supposed to do? Like, I was so bored out of my wits. In fact, right, for IB5, if you're taking HL physics, I will not start lesson until end of February next year. That means I will not see you for October, November, December, January, and February. So a lot of parents always ask me like, oh, but can you teach in advance? And I'm like, no, I don't want to teach in advance. It's so boring after that. Yeah, I don't want to teach in advance. Then it feels like I'm just dragging it out for the sake of dragging it out. I don't want to. Yeah, yeah, lah, I'm not very business savvy that way. Okay, go. Git. Bye bye. Hang on a pass. Bye bye. Bye bye. Hang on, Nash. Come. Yeah, why the heck do you not